So last time we talked about linear transformations. So now we are going to do some more work on linear transformations. Get some more properties of the linear transformations. I believe you found time to read the previous work. So a lot of these things will not make sense if you have not been reading the previous work. So I hope you are finding time to read. Mnasoma mkiwa nyumbani?
Yes.
Yes, sir.
Najaribu.
But you are tight.
Zimiu, wacha mambo mingi bwana, soma. Hakuna tight. Soma. You can find a way around. There's always a way around. If you are really determined to read, make sure you will find a way. So just put in the effort. Think of ways of solving the problem, not being the problem itself. Okay, so we'll proceed with the class. So here it is. So we'll talk about the kernel of a linear transformation. So at this point, the concept of a linear transformation must be clear to you, so that as we go on, everything else will make sense. So suppose we have a map from this vector space Rm to the vector space Rn, which is a linear transformation. So the kernel of the map will be denoted by this. This is a shorthand. So the kernel of T, this is a shorthand, and is defined as follows. The kernel of T is simply a set of all vectors in Rm, which are mapped onto the zero vector in Rn. So that's how it is. We'll see a diagram shortly. So in words, you can say that the kernel is simply all vectors in Rm that are mapped onto the zero vector in Rn by the map. This diagram tries to illustrate that. So the kernel of T should be in Rm. The map takes vectors from Rm to Rn. So all those vectors in Rm, which will be sent to the zero vector in Rn by the map, we call the kernel of the map. So the kernel sits inside the domain. Let's admit someone trying to join. So this picture should give you an idea of what the kernel is. The kernel is this set. Now this kernel sometimes earlier on I think we saw that the zero vector is always mapped onto the zero vector. So one element that must always be in this set is the zero vector itself. The zero vector is always an element of a kernel. There are situations where it is the only element in the kernel. And yes, that can happen. But then there are also situations where there's more than just the zero vector in the kernel. But the zero in Rm, they will be different, because the zero in Rm is different from the zero in Rn. So let's look at an example. So consider this map defined by T x1, x2 being sent to 2x1, 0. So it's a map from R2 to R2. We want to find the kernel. So we want to find all the ordered pairs which are mapped onto the zero vector by this map. So if you pick any vector of this form where the first component is 0 and the second component is x2, then that vector would be mapped onto the zero vector. So it doesn't matter what x2 is, because this map will always assign the second 0 to the second component in the image and multiply the first component by 2. So if the first component is 0, if you multiply it by 2, you will always get 0. And it doesn't matter what is here, because x2 does not affect the image. So any vector in this form will be sent onto the 0 vector in R2. So that tells you that we shall see how to find these vectors. Right now, we are just running through this, but there are techniques to be able to find, to always find the kernel. So any vector in the kernel will look like this. So that we can comfortably say that the kernel of the map consists of all vectors of this form, where the first component is 0, and the second one can be any real number. So any vector of this form will be mapped to 0, and therefore it is in the kernel. Here's another example. So here we have a map from R3 to R3. So I'm picking the first two examples. We have the same values for M and N, but that doesn't have to be the case. We shall see examples where they are different. So again, this is a linear map. In your own time, you can try to check that this is a linear map. This map that takes these vectors to in R3 to this vector in R3. Now, the vector 0, 0, 0 is the only vector that is mapped to 0, right? If any of these numbers is not 0, then there is no way that this vector, the image, can be 0. Are we together?
Yes.
So the only vector, so this is an example where the only vector that is in the kernel is a 0 vector, right? Because there's no way, if any of these numbers is different from 0, then this will never be 0. So the only one that works is this one. Okay. So the kernel in this case consists of exactly one vector, which is a 0 vector. So here is another map from R3 to R2, which is defined as follows: T x1, x2, x3 is sent to x1, x3. So again, this is a linear map. There's an exercise for you here to show that this map is linear. So if we pick any vector in R3 that looks like this, 0, x2, and 0. So the reason we pick 0, x2, and 0 is because this map only picks the first and the third component to set up a vector in R2 in the image. So for this to be 0, for both of these to be 0, or rather for the image of a vector here to be 0, x1 and x3 must both be 0. It doesn't matter what x2 is, but x1 and x3 must both be 0. So if you pick any vector of this form, then we see that such a vector will be mapped onto the 0 vector, right? Any vector where the first and the third component are 0 from R3 will always be mapped onto the 0 vector in R2. So this gives you the kernel of this map. So the kernel of this map will simply consist of vectors that look like this, where x2 is a real number. We don't care what x2 is because it doesn't affect the image. So it doesn't matter what x2 is. As long as this first and the third are 0, then the image of that vector will always be 0, 0. Am I moving too slowly?
Fine, sir.
Oh, I thought you were going to tell me to double the speed. Now, I've requested for the timetable for the exam, but I don't know which date the maths paper will be.
It will be on Friday.
Friday
That's
next week. Huh?
Yes. Yes, Friday next week.
Okay. So I will send a cut out on Monday. You will have maybe 2 days to do it. So I hope you have been reading. Is that okay?
Yes.
It's okay. Good. So the kernel of T consists of vectors in R3 which have this form. I think we have checked that example. So we now look at techniques which can help us to compute the kernel. The previous examples were carefully selected so that you can easily solve them. But now we want to look at the general technique. Suppose you can't easily spot the kernel. How do you solve that? So here, let's consider a map from R3 to R2 given by this. Again, this is a linear map, and you need to show that it's a linear map in your own time. So if we want to compute the kernel of this map, we need to find all vectors in R3 which are mapped onto the 0 vector in R2. Okay. So so let's pick any vector in the kernel. So if a vector is in the kernel, what will happen? It must be mapped onto the 0 vector. That is just by definition. If you're in the kernel, you must be mapped onto the 0 vector. So what you're left with is to find all vectors x, y, and z such that these two will be equal to 0. X plus y will be equal to 0, and 2x plus z will be equal to 0. So now this gives you a system of linear equations as follows. You have a system in 3 variables, x, y, and z. So x plus y is 0, and x plus z is 0. Now you can solve this system of linear equations. And the solution space to this, the solution to this system, all the vectors that satisfy this system will be in the kernel. So let's see, we learned how to solve systems of linear equations. We use the row reduction, which is usually called the Gauss-Jordan Elimination technique. So the augmented matrix is this, 1, 1, 0, 2, 0, 1, if you work it out. Then when you apply the row reduction, this is what you end up as your, I believe this is what you'll end up with as your, you'll double check this, you'll end up with this as your reduced row echelon form, right? If you want to try it out, you can try and convince yourself that that is the reduced. This shouldn't take you long to do. So let me give you that work. Can you find a reduced echelon form of this and confirm that it is exactly the same as this? I think 5 minutes will be enough. Or maybe 2 minutes.
5.
Yeah, so confirm that this, the reduced echelon form of this is exactly what I have. This is the augmented matrix, so just start from this point and apply the row operations. You already have this, so by now you should have tried it out. You got the notes earlier. So if when you're done, you let me know. If you keep quiet, I will not know. So you need to tell me when you're done. So have you finished? Or has anyone finished?
Yes.
Good. So have you confirmed that that is the...
It is.
So this is a reduced Echelon form. So as usual, you need to find your basic variables and your free variables. Z is a free variable, so you try to write all the other basic variables in terms of the free variables, and this is your solution. So any vector in the kernel will look like this. This is a solution to the homogeneous system that we set up, and any vector that looks like this will be a solution to the system, and also will be in the kernel. So you can get any vector in the kernel simply by fixing a value of b. Any value of b that you fix here should give you a vector in the kernel. So can we check if b is equal to 1, we have negative a half, and 1. Will the map take that to 0? So negative a half plus a half will be 0. And if x is negative a half, 2 times negative a half will give us negative 1, and z is 1. So that negative 1 plus 1 will give us 0. So that works if you set b is equal to 1. So you can set b to any value, and you will get a vector that is in the kernel. So the kernel consists of all vectors that are multiples of this vector, negative a half, and 1. Any questions on that? If you like, you can multiply by 2 so that you write out your vector in this form. But any of them is correct. This one is correct. This is also correct. This you only use this if you don't want to work with fractions. I don't know what, I think this. Yeah, I think this is correct. So this is also another way to write the vector, the equivalent. So by changing the values of t, if you keep shifting the t, you will always get a vector in the kernel. So with that in mind, we can describe the kernel as a set in this form. The kernel of t is simply the set of all vectors t, such that these vectors, the multiples of this vector, or rather the set of all set consisting of all vectors that are multiples of this vector, negative 1, 1, and 2. So you can see that the kernel will have infinitely many
Solutions.
vectors, and it will have infinitely many vectors, and it is also a subspace, because in this case you can see it is just a span of one vector. All the multiples of one vector is a span of that vector. And we recall that there's the span of a set of vectors, even if it is just one vector, will give you a subspace. So this gives you an idea of what the kernel is. The kernel is actually a subspace of the vector space. Here is another example. Here it's a slightly bigger space. We have R4 to R3. And we have the linear map defined by this. X1 goes to X1 plus X2. X2 goes to X3 plus X4. And then the third one is just 0. That's it. So we need to find the kernel of this map. Again, you need to convince yourself in your own time, prove that this is a linear map. So the solution, again, is as follows. We need to find all vectors in R4, which are mapped onto the 0 vector in R3. Right? So if we can find those, so that means we need to find those vectors which satisfy these two equations. So again, we have 2 equations in 4 variables. So we can write out the augmented matrix like this. And this is interesting. I think it is already in reduced echelon form, so you don't have to do anything else, but you proceed to find the basic variables. Here, the basic variables will be x1, and the other one that corresponds to a leading entry is x3. So x1 and x3 are the basic variables. Give me a minute. Okay, so I'm back again. So we need to solve this system. Once we solve it, we'll find the vectors that are in the kernel. We've seen that the basic variables in this case will be x1 and x3. The free variables will be x2 and x4. So we have to give x2 and x4 some labels, which we do here. x2, we call it A, and x4, we call them B. And then we try to write the basic variables in terms of the free variables. And when we do that, this is what we get. I think you know how to do this. I have skipped some steps, but this is how you will, this is what you'll end up with, right? Can you confirm that with this setup where x2 is A and x4 is B, that can you work out the solution to this? Then you compare with mine. Eh? You already have the reduced echelon form, so just pick it up from there and write out the solution to the system.
It's correct.
It's correct, yeah? Okay.
Yes.
So this gives you the solution to that homogeneous system. And any vector, if we can write it in vector form as follows. Pick the components that have A, put them on one end, and the ones that have B, put them on one end. So this, any vector that is of this form will be in the kernel. You can get, if you want to get a specific vector, you just fix the values of A and B. So for instance, if A is 0, you will get a value. If B is 0, you will, if A is 0, you will get, or rather if A is 0 and B is 1, you will have 0, 0, negative 2, 1 as your vector. You can check if that vector is mapped to the 0 vector, and therefore confirm if it is indeed in the kernel. But it doesn't matter which values of A and B that you pick. Any vector that satisfies this condition, any vector in R4 that satisfies this condition will be in the kernel. So we have seen again here that any vector in the kernel, in this case, you see the way it is written out here, it means any vector in the kernel must be a linear combination of these two vectors, right? So it means the kernel is equal to the span of these two vectors because all linear combinations of these two vectors will be in the kernel. And therefore, again, the kernel here is a subspace of R4. So that is what we are saying in the next part. And here we are fixing values of A and B. If A is 1 and B is 1, we'll get V1 plus V2, which will be equal to these two, this vector in R4. And you can check that this vector will actually be sent to the 0 vector in R3. And therefore, this vector is in the kernel. And if you want to write out as a set, So the kernel consists of all vectors in R4, which are a linear combination of these two vectors, -1, 1, 0, 0, and 0, 0, -2, 1. So we also make the following observation, that these two vectors are linearly independent. And therefore, there must be a basis for the kernel. Remember, the basis is a subspace. I mean, the kernel is a subspace, and it will have its own basis. The basis for the subspace will be a set of linearly independent vectors that span the subspace. So in this case, these two vectors span the kernel, and they are linearly independent, and therefore will form a basis for the kernel. Are we together?
Yes, sir.
Yes.
It's okay.
So here is a statement that we are now making it formal. We have been making this statement before, that if you have a linear transformation, the kernel is a subspace of the domain. And the proof is here. So how do you prove that something is a subspace? First of all, you need to check that if you pick any two vectors in the set, the sum will be in the set, right? Also, you need to check that a multiple of a vector in the set will also be in the set. So if we pick two vectors from the kernel, it means they must be mapped to 0, right? So we can check what is the image of the sum of the two vectors. If you get the image of a sum of the two vectors, we also get 0, because this is a linear map, and therefore we can split this into TV1 plus TV2. But we already know that V1 and V2 are in the kernel, so both of these are the 0 vector. But the 0 vector remember, this is a 0 vector in Rn, not Rm now, because once you move from Rm, the output will be in Rn. So these two are 0 vectors, because V1 and V2 are in the kernel, and therefore their sum must be the 0 vector. That means we have seen that if V1 and V2 are in the kernel, the sum will also be mapped onto 0, and therefore V1 plus V2, the sum of the two vectors, will also be in the kernel. That is one property to check that's a subspace. The second one is to check that a multiple of a vector in the kernel will also be in the kernel. So T alpha V1 will be equal to alpha TV1. This is true because T is a linear transformation. That's already known or given in the theorem. But we know that TV1 is the 0 vector because V1 is in the kernel. So here we have alpha multiplied by the 0 vector, which is equal to 0 vector. So again, a multiple of a vector in the kernel is mapped to the 0 vector, and therefore it must be in the kernel of the linear map. So from this, we can conclude that the kernel is a subspace of Rm. Are we together?
Yes.
So here is another case. It says that a linear transformation, a theorem rather, the linear transformation is injective if and only if the only vector in the kernel is the 0 vector. So I will not go through the proof of this one, but if you have a situation where the only vector in the kernel is the 0 vector, then that map is injective. You are familiar with this term. Injective means a one-to-one function. You did this in SMA 101. You know what an injective function or an injective map is? Hey, mmeingia kwa kichaka bwana.
Yes.
Okay. So if you don't know, you better go and get the definition, because it's important that you get it. It's easy to get the definition of an injective function. You just Just search for it on Google. Google will tell you, or if you still have your first year notes, you can find that there as well. So here the important thing I hope you have gotten the idea here. If the kernel contains only the zero vector, then that map will be an injective map. The proof follows, but I will not go through the proof. I want you to remember this property, that if you have a map and it turns out that the kernel contains only the zero vector, then that map must be injective. So the proof follows, you can look at it in your own time. But here is an example. Suppose we have a map from R2 to R3, where X, Y is mapped onto X, 2Y, and 0. Then you can confirm that the kernel will consist of all vectors in R2, which are mapped onto the zero vector in R3. And that means you have to set up a system of linear equations where X is 0 and 2Y is also 0, right? Which is what we do here. But this simply results in the only solution here will be that X and Y are both 0, right? So there's no other vector that will be in the kernel. If you look at this carefully, you can see that if any of this, if X or Y is not 0, then there is no way that this vector will be 0. So the only vector that is mapped onto 0 is where both X and Y are 0. And therefore, the only vector in the kernel is the 0 vector, which is what we state at the bottom. So the kernel here consists only of the 0 vector. So from this now, we can conclude that this map is actually injective. It's a one-to-one map. So this map, we can conclude that it is injective because the only solution, the only vector in the kernel is the 0 vector. There's no other vector. So the next thing we'll look at is the image of a linear transformation. This is where we dropped off in the last class. So the image of a linear transformation, let's look at this. Let T be a map from Rm to Rn, and let it be a linear transformation. So the image will simply be the set of all vectors in the codomain here, which have a pre-image in the domain. In other words, the vectors in here for which there's a corresponding vector in Rm, such that that vector is mapped to it, right? So we need to find a vector W in Rn such that there is a corresponding vector V in Rm which is mapped onto W, so that TV is equal to W. I think there's a diagram that will illustrate this better so that you'll see the image. But we shall denote the image of T. This is a shorthand, Im and T. This is a shorthand for the image of T. Tuko pamoja? So here is nothing but notation and definition. And like I told you, it is very important that you get these definitions right. If you do not read these definitions and understand them, you will see stars. Mnasikianga ile blue stars. I'm not trying to discourage you. I'm just trying to tell you the truth about university mathematics. It's no joke. You really have to take it very seriously. If you're given a definition, spend time and go through all that English. There's a lot of ile mnasemanga kizungu mingi. Iko na kizungu mingi, but you have to go through that kizungu. It is really important. If you get it wrong, you can get a whole question wrong just because you got the definition wrong. So here is a shorthand. The image of T is denoted by this, IM and then T. And you can describe it in terms of sets. It means you get all vectors in Rn such that there exists a vector V in Rm, which is mapped onto that vector. So any vector for which there is a pre-image, for which there's a pre-image will be in the image. So when you're working with functions, I think this is what you would call the range of a function, right? So here is an example. So T is a map from R3 to R2, and it's defined by this, and it's clearly a linear map, though you should be able to prove it in your own time. Another example to check that it's a linear map. Now then the image of T will consist of all vectors of this form, x0 in R2. So this one is easy to check because you can see what the image, the way it is constructed is carefully selected so that you can quickly see what the vectors in the image will look like. They'll look like this. So the image simply consists of all vectors of this form. So any vector for which y is not equal to 0, any ordered pair from R2 for which y is not equal to 0 will not be in the image, because the way it is defined, the y component of the image must always be 0. So for the vectors like 1, 2, 0, 3, and 7, 10 would definitely not be in the image because 2, 3, and 10 are not equal to 0. Anything in the image must be of this form. So this diagram tries to explain. I made it too large. Let me reduce it. So this diagram tries to explain to you what the image is. So here we have a map. The map takes things from this vector space Rm and sends them to this vector space Rn. So if you're looking for the image, you need to be able to find it will consist of these vectors W, for which you can find a corresponding vector V in Rm. Any vector for which you cannot find a corresponding vector in Rm will not be in the image. So it's possible that the image will not be the whole of Rn. It can be only a part of it. It can also be the whole of Rn, that's fine, but the situations where the image is not the whole of the codomain. So this is what you would call the range in SMA 101. So this shaded area, the red part, is not in the image. The image is just the part that is shaded with the blue lines. So this statement says that it's also possible for the image to be the whole of Rn. And if that is the case, if the image is the whole of Rn, then your map is surjective, right? You remember the definition of our surjective map? Can someone define for us what is a surjective map? If you define this correctly, you get an instant, you get what? 70 MB.
Onto.
That is not a definition. That is another name. Like if I ask you who is Aaron, you say Kisaka. So you need to describe yourself. So onto is just another name, another way of saying surjective. It's not a definition of surjective. It's another name for the same thing. So can you define what does it mean when we say a function is onto? Hii imewashinda bwana. Looks like I will keep my 70 MB.
Let me try.
Okay, try. Is it Chege who's trying or Cleophas?
First,
Okay, go ahead.
a surjective transformation is said to be a surjective transformation is the one such that when it runs from Rm to Rn, the outcome, the kernel of the transformation is a zero vector.
That is an injective transformation.
Oh, this one is a surjective.
We're asking about surjective. And even what you have given is not the definition of injective. That is a consequence. It's just a theorem that can help you to check when something is injective, but it's not the definition. What you can do is this. These definitions for an injective function, because this is basically a function, the definition of an injective function is on the internet. All you needed to do now is go to the internet, look for the definition of an injective function and read it out to me. You would have gotten 70 MB. This is not the exam, so you are free to check. Don't try to create your own definitions. These definitions exist. Okay. And the one you're giving me is unlikely to be the one you're given in SMA 101. The one I'm looking for is the one you're given in SMA 101. Or at least the one you can look for on the net.
A function f from a set x to a set y is surjective if for every element y in the codomain y of f, there is at least one element x in the domain x of f such that fx is equals to y.
Yes, that's correct. So Kisaga.
Yes.
You want to take away all the MBs, man. That's not fair.
Unaweza patia Cleophas.
Cleophas?
Yes, sir.
Kisaka has donated the MBs. Okay, both of you will get for trying. Just make sure you claim them.
Okay.
So most of these definitions are easy to find. So if you come across a term that is not making sense, simply go to the internet, look it up. You will find there are a million places you can find these definitions. And read the Kizungu in it. Don't just ignore it. Take time, read it, and get the Kizungu correctly. They usually come with a lot of Kizungu mingi. So the next thing we need to do is the question at hand now is, how do we find the image of a linear transformation? So this one was easy to see. The first example we did was easy to see because of the way it is set up. The image will simply be vectors of this form, where x is a real number and the second element is 0. Now this is an example that is not surjective because we found some elements in the codomain which do not have a preimage, right? So this 1, 2, 0, 3, and 7, 10 are not in the image. So it means the image is not the whole of R2, and therefore this map is not surjective. This is an example of a map that is not surjective. So these vectors like 1, 2, 0, 3, and 7, 10 would fall in this red region because they are not in the image. And therefore, that map is an example of a map that is not surjective. Nego? Good. So it is possible. Yeah, this is just defining surjective map. So how do we find the image? Given a map, how do we find the image? Suppose it's a case which is not as simple as this, because this one you can just quickly tell the image by observing. What if it is not that simple? How do we find the image? So let's look at this map from R3 to R2. It's defined by this transformation. X, Y, Z is mapped onto X plus Y and 2X plus Z. So it's a map from R3 to R2. So what we are looking for is a subset of R2. The image must be a subset of R2, and we need to find it. So we know the kernel. The kernel is this one. We have worked with this map earlier, and we showed that the kernel is made up of all vectors that are multiples of this vector, -1, 1, and 2. Is that correct? I think we did this earlier. So I'm just hoping that I have copied the kernel correctly. But if I haven't, you can go back and check. And in any case, you now know how to find the kernel, so you can compute your own answer and compare with this one. So we need to find the image. Remember, the kernel will be a subset of R3. So it's made up of vectors, which are multiples of this one, -1, 1, and 2. Tuko pamoja?
Yes.
Good.
Yeah.
Now, to find the image of T, we need to obtain the matrix of T with respect to the standard basis. Remember, we learned how to do this in the last class. Given a map, you can find the matrix with respect to the standard basis. So the required matrix is this. Can you find this matrix? Let me give you that work. Can you find the matrix of this linear transformation with respect to this basis? Just find it so that we can compare it with the answer we have, and also gives you a chance to test your knowledge of from the previous class. Can you find the matrix?
Let's try.
Okay. I'll give you 5 minutes. Maybe 2 minutes. 5 may be too much. So let's work with 5 minutes. We resume in about 4 or 5 minutes. Or if you find it earlier, if someone finds it earlier, you let me know.
It's that matrix.
So I hope everyone else has confirmed also.
Not yet.
Okay, just a few more minutes, then we can continue. So just check that you have the same matrix as the one we have here. So it means if you want to get this matrix can replace the linear transformation. Is there anyone who has a question on this before we proceed? So do you have a question on this?
No.
Okay, so this is the matrix. Now, anytime you want to work out the transformation, you can replace it with this matrix so that this matrix multiplied by this vector will give you an element in the image. So if you look at this carefully, this this whole thing can be written as in this form: x multiplied by 1, 2, y multiplied by 1, 0, and z multiplied by 0, 1. Right? So anything in the image, because to find anything in the image, you simply multiply a vector in R3 by this matrix. But that you can work it out like this as well. So any vector in the image is simply a linear combination of the vectors in the column of this matrix. Right? So that's how you interpret it. The image is just a linear combination of the vectors which form up the columns of this matrix of the linear transformation. So that's how we write it. So any vector in the image will be this linear combination of the three matrices, vectors, 1, 2, 1, 0, and 0, 1. So now this, the image of T therefore will be the set of all linear combinations of these three vectors. Now we can reduce these vectors because they are linearly dependent. You can see that V1 is the same as V2 plus 2V3, right? So we don't need V1. The vectors V2 and V3 are linearly independent, and that's all we need, right? So the span of this set is the same as the span of just the two vectors, 1, 0, and 0, 1. Based on that, we can say that these two vectors, 1, 0, and 0, 1, will form a basis for the image. We already know that these two vectors span R2, so it means our image will be the whole of R2, right? Because these two vectors that span the image turn out to be the same two vectors that span the whole of R2. So our image is just the whole of R2. So here's an example of a linear map that is surjective because the image is the whole of R2. So the image of T will be equal to. So what you will also notice is this could easily have gone either way. You could also have picked this first vector and the second vector, right? Because you can pick this last vector, V3 can be written as a linear combination of the first two vectors. The same way I could have picked the third vector and the first vector. Those two also will still form a basis for the image. Can you see how that works? But I picked the ones that are easy to work with, 1, 0, and 0, 1. So we get that the image is the whole of R2 in this case, which is made up just of a set of vectors, which are a linear combination of the two vectors 1, 0, and 0, 1. Okay, that's an example of a map that is surjective, and we found the image. We can take a 5-minute break, then we proceed to the next part. Is that acceptable?
Yes.
Yes.
I think we can now continue. Wale walikuwa na kunywa chai wamemaliza sasa.
Wamemaliza.
Okay. So we do another example. So it says let T be a map from R4 to R3 defined by this. We need to determine the image of T. So the first thing we do is to find the matrix of the transformation using the usual style. So the matrix turns out to be this matrix. The last two columns are 0, and the first two columns are 1, 1, 0, and negative 1, 1, 0. So the image of the map is given by the set of all linear combinations of the vectors in the column, right? So we consider all possible linear combinations of the vectors in the column, and we realize that we can ignore the last two because they are both zeros, and the image will simply be made up of the linear combination of these first two vectors, 1, 1, 0, and negative 1, 1, 0. So the image is made up of all linear combinations of these vectors. So these two vectors, you can see clearly are linearly independent, and you can confirm that. And therefore, they are linearly independent, and they span the image, and therefore they form a basis for the image. They span the image because we have established that any vector in the image must be a linear combination of these two vectors. And therefore, we can write the image of T to be the set of all linear combinations of these two vectors, where A and B are real numbers. So this gives you the image. It's a set of many. It's a set of many. It consists of many vectors, where the vectors are just linear combinations of these two vectors. So we have the next one here. This one is a little bigger. We have, it has more interesting equations in here, R4 to R3. That's the map. So this is a linear map. You can verify it in your own time that it's linear. The question at hand is to determine the image of the map. So the first thing you do here is to determine the matrix of the linear transformation with respect to the standard basis, and that's the matrix. We put it in reduced echelon form as follows. So when the matrix is bigger, this technique works better. So we put the matrix in reduced echelon form, and when you do that, this is what you have, right? So when it is in reduced echelon form, you can see these first two columns are the only ones with leading entries. So this one and this one, and they correspond to X1, and they correspond to the first two columns of A, right? So when you observe this, just pick any column that corresponds to a leading entry. Sometimes they may not be in sequence. You might find that the leading entry may be in the third column. Along the second row, it may be in the third column. So those are the columns you'll pick. So simply pick any column that has a leading entry, and then the image will be made up of the linear combinations of the corresponding columns from the original matrix. So now once you find those two that have leading entries, find the corresponding columns in the original matrix A, so that the image now will be the span of these two vectors. So the image of the map consists of the span of the first two vectors. if we were to write that in as a set, the image of T now will consist of all linear combinations of the first two columns of the matrix of the linear transformation. So why the first two columns? Because it's only these first two columns that correspond to leading entries. You can see there's a leading entry here and there's a leading entry here. So if the leading entry was here, we would pick the first and the third column of A to be the the vectors that span the image. Are we together? Now it turns out that these two vectors, 1, 1, 1 and 1, 0, 1 are linear independent, and therefore they are linearly independent and they span the image, and therefore they form a basis for the image. So what we have not proved is that the linear and the image of a linear transformation is also a subspace. I think maybe it comes later. So can you try to solve this? This is not the one we have solved, is it? No. Can you solve this one? Find the image. So you remember the procedure. You will find the matrix for the linear transformation, convert that matrix into reduced echelon form, and then pick the columns that have the leading entries, and the corresponding columns in the matrix of the linear transformations will form a basis for the image. Are we together?
Yes.
Yes.
Good. So now solve this one.
One, 1, 0, and 0, 0, 1. . 1, 1, 0 and 0, 0, 1. 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 1,
So that looks correct. Now, the other thing maybe I should mention, because the only thing you're looking for are the leading entries. Even if you stopped at this point where it is in echelon form, it doesn't have to be in reduced echelon form. Echelon form alone is enough to find the leading entries that you're looking for. So you could also just stop here and find your leading entries and pick the column. So this one tells us that we should pick the first and the third column because that's where we had the leading entries. So, but not the first and the third column of this matrix. It will be the first and the third column of the matrix of the linear transformation. So the basis, the basis for the image will simply be this first column and the third column. I don't know who answered, but they answered correctly. Who was that?
Isaac.
Yes, the famous Kisaka. So these two vectors will form a basis for the image of the linear transformation, and any vector in the image can be written as a linear combination of the two vectors. So if we were to write this out as a set, it means that this is no. Why do I have three? Actually, there should be three, correct? Because we have three leading entries. Or did I make a mistake somewhere? There's a leading entry here as well. So it's the first, the second, the first, the third, and the fourth. So that means we pick these three vectors, 1, 1, 0, 0, 0, 1, and 1, 3, 1. Those three vectors would give us a basis for the image. So these three vectors, 1, 1, 0, 0, 0, 1, and 1, 2, 1, from the original matrix, not from the raw reduced matrix, will give us the basis for the image. And any vector in the image can be written as a linear combination of these three vectors. Now, also, you will notice that these three vectors are linearly independent. And any set of three linearly independent vectors will form a basis of R3, right? So it means the image is the whole of R3. And therefore, this is another example of a map that is surjective because the image is the whole of R3. Unaona hiyo kweli?
Yes.
So the image is the whole of R3 because the basis consists of three vectors from R3. And we know that the dimension of R3 is 3. So any set of three linearly independent vectors in R3 will form a basis because the dimension of R3 is equal to 3. So here is a theorem I had mentioned earlier. It says that if you have a linear map, then the image of the map is a subspace. It's a subspace of Rn, not T. It's a subspace of Rn. So change this, make this correction. This is page what? Page 20. I think it's a continuation of the other notes. So on page 20, this should be a subspace of Rn because T is a map. T is not a vector space. So you can't say a subspace of T. It must be a subspace of a vector space. So this should be, the correct thing is this Rn should replace the T. Again, the proof is here, but we shall not go through the proof. Just remember that the image will always be a subspace. Now we can also consider composition of linear transformations. This is similar to what you did in when talking about functions. You must have done composition of functions. Mnakumbuka?
Yes. Yeah.
So let's look at an example. Suppose we have a map T from Rm to Rk and S from Rk to Rn. Then we can get this composition, S of T. S of T simply means T acts first, then followed by S. So if T acts, T will pick a vector in Rm and send it to Rk. Now from Rk, S will pick a vector in Rk and send it to a vector in Rn. So for this composition to make sense, these two things, this Rk, these two must be the same thing. Otherwise, you will not be able to do this. Because for it to work, you must have T sending vectors to Rk, and S will pick up from Rk to send the vectors to Rn. Yeah. You can hear me?
Yes, we can hear.
Yes.
Lakini hamuelewi nasema nini?
I'm with you.
Okay. Now it's also possible. This is just for two transformations. It's also possible to obtain the linear transformation of more than one transformation, as long as the domains make sense. The domains have to make sense. They have to be compatible. The domains and codomains, they have to make sense. So here is an example. We have two maps. T is a map from R2 to R2, and S is another linear map from R2 to R3. So this means we can get the composition of S and T, because S of T simply means T acts first, followed by S, so that T sends vectors to R2, and S will pick up from R2 and send the vectors to R3. So we define these two linear transformations as this: Txy sends vectors to 0y, and Sxy sends vectors to minus x minus y 0. So we can now let's obtain the composition of S of T. So how it works is that T will act first. So T will act, since T is acting, it must act on a vector in R2. So T will act on this vector, xy. So S will pick up from the image of this vector, xy, under this linear transformation T. So xy will be taken to 0y by T. And S will take 0y to 0, negative y, 0. So if we relabel this composition as Q, so Q is a composition of S and T, then we have a new linear map which takes xy to 0, negative y, 0. So this is just a composition of S and T. That's the map. So I need to know that you are following up to that point. Ama mmepotea?
Hapo nimepata. Wote nimeelewa vizuri.
Kwa sawa.
Leo mmeiva kweli kweli. So we continue. We obtain the matrices for S and T with respect to standard basis. So we know how to find the matrices of a linear transformation, and we have two of them. We have two linear transformations, that is T and S. So since you know how to find the matrices, I will just go ahead and state the matrices in what follows. So the matrix of transformation for T with respect to the standard basis will be this. You can check that later. And the matrix for S will simply be this matrix. Now, what happens if you already know the matrix of a linear transformation of T with respect to the standard basis, and also for S with respect to the standard basis, you can find the matrix of a linear transformation of a composition of S and T just by multiplying the two. Since T is the one that acts first, it's the one that will be on the inside, then followed by S. So if you multiply these two matrices, you will end up with the matrix of a linear transformation Q, which is a composition of S and T. So if you want to get the matrix of a composition, and you already know the matrix for S and the matrix for T, all you have to do is multiply them, and you will get the matrix for the composition. But you can double check that, because now initially we didn't get the matrix, we just found the transformation, the composition itself. It picks X, Y, and sends to 0, negative Y, 0. You can confirm that the matrix for this will be exactly the same as the one we have obtained down here. So that's the matrix of a linear transformation, which is a composition of S and T. So look at the order, because we have composition of S of T. Since T acts first, you'll have the matrix for T on the inside and the matrix for S on the outside. And the product will give you the matrix with respect to the standard basis for the composition of S and T. Q is just a composition of S and T. Remember, we renamed them. We renamed it here up earlier. So this now is just explaining what we have done. And also explaining it for more, when you have more, what do you call them? If you have more than one, if you have a composition of more than one linear transformation, it is possible to get the matrix just like the same way. You just extend it to more linear transformations. So there's one example that I'm looking for before we stop. Where is it? It was 3. Part 5, this is one. What is this one? So there's one section for square matrices which you want to cover now, and then that will be the last thing to do. Let me share the screen for that, then we can work on that. So basically we want to see how we compute the determinants. So, although I don't know whether we should cover this. So what I can do, given that we are, instead of adding new material, what I can do, I will share these notes. But this last bit on square matrices, I will not examine you on that. This last bit that I'm going to share. I suggest that we stop at this point. But the part which I wanted to share, I will share the notes. Then you can read for your own information. But so that bit will not be examinable. There's a part where you are just learning how to find the determinant of a square matrix. I think that is useful for you. Probably also useful in other subjects that you're doing, like economics. But given that we have not much time remaining, I don't, that will not be examinable, but it will be shared. So the last lecture I'm going to share, the notes that I'm sharing, will not be examined. Unless you want it examined. Maybe you are thirsty for questions. Maybe you'll be feeling shortchanged. You want all the topics. Now you need to ask some questions now. I've been the only one talking, man. I need to give you the stage.